Okay, let's make this quick, because I have a lot of papers to correct. Okay, do we have questions on every section?
No.
Yes.
Yeah.
Wait, not every section.
Can you like go over 17.2 and 17.3 like the lecture?
It's on the video, Wang!
I need
Yeah, but
help.
like some.
I watched the 17.1 part.
Okay, you know, the answer is no.
The lecture or the
Hey, you guys think you guys missed class? It's a jolly holiday, right?
But we didn't.
It's not a holiday.
Mr. Park, we have apps due this week.
Well, if you wait to the last minute, then you deserve what you get.
What? Yeah, why can't we get it next time?
Yeah, can get
We only do one, you know how easy it is to do one section a day?
Wait,
So
but there's
hard.
no solution key.
Yeah.
There
I agree
is.
with Jason.
What do you mean there's no solution key? He literally gave it to us.
You mean?
Oh, ants. Sorry.
I gave-
Read the ants.
Yeah.
Okay, wait. I think I have a book somewhere
Okay, let's.
that has the solutions, but you guys gonna have to come in.
No.
And
You
what's
know, I see I forgot about this book. I went to the McKinley Book Fair like 8 years ago. I just happened to be there. And they were selling this book for 50 cents.
No
So I
way.
bought it.
That is an antique.
I'll buy it for you for $1.
No, it's called Stay in the
It's
Room.
net profit, yeah.
So like what chapter are we doing now? 14.
17.
17.2.
17.2 already.
Can you, Mr. Park, some of the answers didn't come out.
See, look,
Yeah, see.
they don't just have answers in here, they have the solutions.
Yeah, can I?
So you know what, I'm just gonna leave it on the table in the back of my room, people on the video. And if you guys wanna come in and look at it, you can. I forgot all about this, I'm glad somebody said something.
Okay, 17.2.
Okay, so are you saying we don't need to do 17.1?
No.
Yeah, no, 17.1.
Ah, then I gotta scroll.
Yeah, sorry.
Ooh. I really want my smart board back.
What happened to it?
Well, they tricked me. They told me, well, if all you do, if you don't like, write on it and stuff like that,
Hey, can you open this for me? My phone is spraying, so I can't open it. I just spin it from dodgeball earlier.
Are you serious?
okay, which problems are we doing at 17.2?
Number 3.
Number 3.
What?
Number 5.
Basically a lot of them.
Where?
Oh my goodness.
Number
This
9.
didn't turn out.
No, number 9. You see, it just didn't come out.
Wait, did you get number 3? I got 3t squared minus 2t4 minus.
T, you're not supposed to have T.
Oh, oops. Never mind.
So,
Wait, time out. Didn't I do problems from this?
No. You didn't.
Yes, I did.
Can you do number 11?
Yeah, let's go in order, let's go in order. And let's go number 3.
Okay, wait, where's the formula first of all?
You didn't get a t at all.
Gradient F.
Gradient of f dot
Dot
u.
u.
Come on.
I did that.
Okay, what's the first number?
3.
Oh my goodness. Okay, here we go. Number 3, find the direction, the derivative at the given point in the direction indicated. Number 3. So, a function of x and y is x e to the x. Gosh, I can't even see that. Except see that's e to the y. Minus y e to the x at the point 1, 0 in the direction of 3i plus 4j. I'm just going to write the vector like that. So first we got to compute the gradient, which is,
Sorry. Is it 17?
17.2.
Oh, I copied the problem wrong.
Oh gosh, too bad we're doing it already.
Yeah.
And here, Wayne, watch, since obviously we didn't do it.
yeah.
It's e to the 1,
E to the y, comma.
negative e to
No, that can't be right.
Oh,
What's
sorry,
the
sorry. I'm
Partial with respect to
Minus.
x. Minus,
y e to x.
comma, not partial with respect to y.
X e to the y minus e to x.
Okay, correct. So at the point 1, 0, what is the gradient at that point? If I plug in 1 for x and 0 for y, what do we get?
1.
1,
Comma.
comma,
Negative.
1.
1.
1.
No, 0.
Wait,
Oh, no.
it's not-
No, 1 minus E.
Yeah, 1 minus e, what are you guys talking about?
Hey, that's-
1 minus e, wait,
are you-
1 minus 0, 1 minus e, okay, that's correct. And then, if this is the direction we're doing it in, we need a unit vector. What is the length of this vector?
5.
5, so to make it a unit vector, multiply it by 1/5, right? So shall we go 3/5, comma 4/5? And then all you have to do is take the dot product of these two vectors. So this times this is 3/5 plus 4/5 times 1 minus e. I will leave the simplifying to you. Pretty much all you can do is add 3/5 and 4/5 to get 7/5.
Minus 4.
Yeah. Okay, that's number 3. What's the next problem?
11.
Oh no, I gotta scroll.
No, number 5.
Oh gosh. Okay, let's do 5. I don't need to scroll. 5. So our function is ax, well, I like the kind with letters in it. Because x and y at the point 1 comma 1 in the direction of 1 negative 1. All right. So first we compute the gradient, which is Cho, x component of the gradient.
Wait. Wait, you know the I minus j stuff? That's like the I with the
Hat.
Yeah,
Yeah, but we don't need that. You don't need to put the hat because see how it's boldface?
Yeah, but like it would be. if
Yeah.
you already have it.
Yeah. But I rather write the vector like this, you know, using this notation. But it's up. You can write it whichever notation you want.
Any x minus.
Okay. So wait. I can't look at it and tell you what the answer is. So why don't we actually do it? Low d high minus high d low.
Oh, but the denominator is very low.
We're taking the derivative with respect to x, right? All over denominator squared we go. So what is that going to be? Ax plus ay minus ax minus by. Ax is cancel out. So you have ay minus by all over x plus y is quantity squared. Did I do that correctly?
Yes.
Yeah.
And then now you take the partial with respect to y. Low d high minus high d low all over denominator squared we go. So that's bx plus by minus ax minus by. The by's cancel. And so you got bx minus ax all over x plus y quantity squared. Correct?
Yes.
So at the point 1, 1, the gradient is, what happens when you plug in 1 for x and 1 for y?
Zero.
What?
E
You
minus
get
y
minus
over 4.
b
Alright.
all over 4.
You got the third guy?
And then b minus a all over 4. Correct?
Mhm.
And then here's the direction of the vector. What is the magnitude of it?
Oh,
Radical 2, so if you multiply by 1 over root 2, you get 1 over root 2, negative 1 over root 2, and then you compute the dot product. So multiply the x components, a minus b over 4 root 2 minus b minus a over 4 root
Oh.
2, and I will leave the simplifying to you.
this part.
It's all computational.
I copied all these problems wrong.
Are you serious?
No, so for this one, for the vector, I put like the one above, which was 1 minus root 3.
Wow.
And for number 3, I put x minus y ex. So,
Alrighty then.
Just do all of them then.
We're not gonna do all. It's all computational, you gotta practice the computations. Okay, number 11, find the directional, come on!
Wait, so that's like the final answer for 5?
No, you gotta
Oh.
simplify it.
Yeah, well, no, you gotta simplify it though.
Oh, yeah.
Find the directional derivative at any point x, y toward the origin. Okay, I gotta think about that. Because we need a direction, yeah? Oh, I erased it. Too bad. So number 11. Find the directional derivative of natural log. Remember, log means natural log, yeah? Square root of x squared plus y squared. We established this several weeks ago. This book uses LOG, but that means natural log.
They said that? No way. I'll just accept.
Yes, you need to accept it. At any point xy, as long as it's not 0, 0, towards the origin. So that's the thing. How do you get a vector that's pointing toward the origin? So, for example, in 2 dimensions, if you have this graph, but it's not 2 dimensions, it's toward the. So how would you label this point right here that lies on the graph? How do you label this point?
X.
XY.
Oh, X, oh,
Yeah, but
root.
I guess you would label it x, y, natural log x square root of x squared plus y squared, right? Right? But when you pick the direction though, you're only doing it in 2 dimensions. So basically, it's from the point xy to the origin like that. So how do you componentize that vector right there? Negative x, negative y. Okay, then you just do the same thing that we do. So first you compute the gradient, which is, now you want to take the 1/2 and put it in the front to make things easier.
Yeah.
Okay, so put the thing in the front, so you get that. So what do we got? 1/2, 1 over x squared plus y squared times 2x, comma, 1/2, 1 over x squared plus y squared times 2y. 2's cancel out, and you get x over x squared plus y squared, y over x squared plus y squared. Okay, and the directional vector would be what? What's the unit vector for this? What is the magnitude of this?
Root x squared plus y.
Okay, so it's going to be negative x over root x squared plus y squared, comma, negative y over root x squared plus y squared. And then you compute the dot product. So that's going to be negative x squared over x squared plus y squared to the 3/2 power, minus y squared all over x squared plus y squared to the 3/2 power. And so if you make a least common denominator of x squared plus y squared to the 3/2 power, the numerator is going to be negative x squared plus y squared quantity, yeah? And of course, all of this will simplify to negative 1 over the square root of x squared plus y squared.
Oh yeah, I see.
Oh, really?
It's the third in the step where you stop putting the equal sign. That's when you did the dot product.
No, this equal sign is this vector equals this vector. This
Yeah,
is the
the
simple
next
part.
one is when you did the dot product. Right?
Yeah, so then you gotta take the unit vector of the directional vector,
Okay.
and then you take the dot product of the gradient with the directional vector.
Where did you get the 1/2 from? 1/2 natural, yeah.
Wait,
E
yeah.
square root, it is L.
Because it was square root, right? When you have a square root, isn't that the same thing as 1/2 power? And then when you have a logarithm, you can put the power in the front, yeah? Just to make it easier to take the derivative.
Wait, how did you get the square roots in the denominator?
Because you gotta make it a unit vector. See this vector here? You gotta make it a unit vector that points in the direction of this.
But how do you make the unit vector of this?
What about the first 2 problems that we did?
No,
No, like,
it means
X
like,
and
cause
Y.
this x and
Yeah,
y is just a
yeah.
variable, so how do you know like?
Yeah, because it's at any point, it says, at any general point x, y, not at a particular point. Here, like here, remember, okay, if you have this vector, what is the length of this vector?
Oh, got it.
So how do you make it a unit vector? Yeah, you multiply by 1/5, right? Like that. So whatever the length of the vector is, you multiply it by 1 over the length of it, yeah? Okay, any others on this?
19.
Determine, okay, did you guys read the thing that goes along with this thing? Determine the path of steepest descent?
We didn't even read the question.
Woo! Okay,
Make it look at.
turn to, those of you following on the video, turn to page 705. Look at the box. A differentiable function f increases most rapidly in the direction of the gradient. The rate of change is then the magnitude of the gradient, and it decreases most rapidly in the opposite direction. You guys get it? It increases most rapidly in the direction of the gradient and decreases most rapidly in the opposite direction. Okay, I think they had a pretty good example in the thing. Okay, that's okay, we'll just do it. What number are we doing? Number 19? Well, 19 and 21 is like the same thing with different numbers, right? So we'll just do 19. You guys can try 21 on your own. So number 19. Determine the path of steepest. Okay, so here's the curve. Z equals x squared plus 3y squared. Okay, what is this graph? Let's review. Park, what is this graph?
Quadratic cone. Wait, is that quadratic cone? Oh, wait, no,
Hyperbolic
it's
cylinder. Wait, what is that?
it's a elliptical
Hyperbolic
cylinder. No.
Elliptic paraboloid.
Elliptic paraboloid. So it's literally like that.
Hey,
Oh,
sure, but
I
read
went-
one.
So during my conference, I went to the Museum of Math in New York. And then they had this thing which generates a hyperboloid of one sheet. Here, let me show you to you. I got it on my iPad.
Wait, you took the video with your iPad?
Oh, my wife took a
Oh, you
video.
went with your wife?
Yeah.
That was like a teacher.
So when I saw that, I said, oh, I gotta show you guys this. Okay, how, I gotta figure out
You can show us the thing.
camera roll, is that it?
Oh my god.
Oh, darn it, it's on my wife's phone, never mind.
Tell her
I'll have her send it to me somehow.
Text it to her right now.
Anyway, let me describe it to you.
Okay.
So, it's like this, they have a, okay, so they have this thing, and like this, and it has all these equally distant things around there. So you climb inside it, there's like a chair, you sit on the chair, and then the chair rotates, yeah? So what happens when you rotate it, this thing is fixed on the top, and then when you rotate it, then these wires, they start to like
Oh, that's
cross, yeah? Can you imagine that? So you sit on this thing, and you rotate it with your feet, and then the top stays constant, but the bottom is spinning. So what happens is, you get something like, I'm trying to think how it's gonna look.
like the hourglass.
Oh,
And you're sitting.
okay, that's ugly. Yeah, so you're sitting, so you're spinning, but then when the bottom spins, the top stays. So what happens is these strings go in like this, and what happens then you end up with like a hyperboloid of one sheet.
And you did that, you sounded something.
Yeah, and I had to do it like 3 times because my wife was not taking the correct picture. Yeah. So she's only taking me, but I said, no, we gotta see the hyperboloid, so we have to do it several times for the topic.
Wait, why don't you just video it?
She did video it.
We're still getting him in the frame.
Oh.
Yeah, but I said, we gotta see the hyperboloid part, that's the important part.
You could just stand for that.
Okay, anyway, can we do this problem? Number 19, determine the path of steepest ascent along the surface from the point 114. So the path of the steepest ascent would be along the gradient and then gonna be the opposite direction, right? So the first thing we're gonna do, think of this as f, compute the gradient. What is it? 2x, comma,
Why?
6y. So at this point, 114, wait, is this gonna be a 3-dimensional thing or a 2-dimensional thing? It's gotta be a three-dimensional, oh, so this is like today's lesson, kind of, yeah? So you know when you have the z like this, you know what you do? You make one side 0, like this, and you move the z to this side like that. So now you have a third component like that. Was there an example in the book that did this? Do you guys even look at the examples? So then what? What would the partial with respect to z be? -1. So at the point 1, 1, 4, what is that vector? So at the point 1, 1, 4, the gradient would be what? Plug in 1, 1, and 4.
2, 6, negative.
2, 6, -4. So that would be the path of quickest ascent, right?
I thought it was -1.
Yeah, it's -1. So then the path of steepest descent would be the opposite of that, which would be -2, -6, 1. Is that the answer? Since the answers are in the book.
Number 19,
Yeah.
17 says
Its projection onto the xy plane is the curve y equals x squared.
x cubed. from
What?
1, 1 to 0, 0.
What?
What?
There's like no point. It's an equation.
Why have you seen a solution?
Good night.
Okay, you know what? We're skipping that problem. We'll come back to it. No, we're not skipping it for the test. We're just skipping it for now. Okay, what about 17.3? Any questions on that one?
A lot.
What?
Actually, no, not a lot.
We went through this. Isn't this just
I just didn't want to read the word problems.
Boy, okay, so basically what you have to know for this problem is, for this section, right there, the chain rule. The derivative with respect to t of f of r of t is the gradient of f of r of t times r prime of t.
Yeah.
Okay.
Number 7. You're gonna have to do the circled ones, right?
Wait, don't do
Yeah, the
number
starred ones. The starred ones. The ones with stars on them.
Wait, there's no solutions. It's only examples.
Oh, okay.
I just want to take time.
Well, maybe that's why we never brought it up.
Number 7.
Okay, let's do number 7.
I want to video.
Just do everything. Number 7, number 9, and number
Okay, wait, number 7.
8. Yeah.
Okay, it says find the rate of change of f with respect to t along the given curve, so that means we're going to use the chain rule of 7. So number 7, I'm trying to read this. U equals x squared. Oh, no, the directions are different for this problem. X equals cosine t, y equals sine t.
Yeah.
So we need to compute du dt. Well, did you look at this in the notes? Oh, I have to walk back and forth. My legs are tired enough as it is. Okay, for those of you following on the video, look at page 713. Does that look familiar from last year?
Last year.
Oh, yeah, I think you're right.
Okay, let me explain. Last year in BC calculus, when we did two-dimensional calculus, like dy dx, wasn't that equal to dy dt times dt dx, because you can treat it like fractions?
Is there a proof of this?
Yeah.
You asked me that last year, remember?
Or like for this?
Dy dt over dx dt. Same thing, right? You can treat it like fractions. So, look at that. In the two-dimensional case, here, I'll just write it over here. Du dt is equal to, look at that. Du dx, oh, that's the partial, sorry.
It's okay.
Partial of u with respect to x times dx dt plus the partial of u with respect to y times dy dt. That looks suspiciously just like this.
Wait, how do you? What?
I don't know, but look at the book. I mean, did you read this? Lots of times they don't have a proof, and then lots of times they say the proof is beyond the scope of this course. But I'm sure you guys don't even read that, yeah?
We're just too lazy.
Okay, so following this rule right here, let's just see if we can follow the rule. Du dt is equal to, okay, what is the partial of u with respect to x? Here's u. What's the partial of u with respect to x? 2x minus 3y, okay, times dx dt. Negative sine t. Plus the partial of u with respect to y. Okay, what's the partial of u with respect to y now? Negative 3x
Plus 4.
plus 4y times dy dt, which is cosine t. And do we have to compute it at a certain point? I'm gonna scroll back to the problem. Okay, I forget what problem we're doing. They're number 7. It says find du dt by the method of dissection. I guess that's the answer right there then. They don't give you a specific point. Is that the answer in the book?
No, it's like negative 3 cosine 2t plus sine 2.
It's super
Say that again?
Yeah.
Negative?
Oh, okay, okay. Well, okay, you want me to simplify this? Negative 2x sine t plus 3y sine t minus 3x cosine t plus 4y cosine t.
The y cosine sine t can mush together.
What are you talking about?
7y sine t.
What?
Oh no, my sorry.
No.
Sorry, no, my.
I think it's
You can't really do anything with that. Okay, what does the answer say? Tell me the answer.
sine 2t minus 3 cosine 2t.
Minus 3 cosine 2t.
How do they do?
Oh, so what they're doing is writing everything in terms of t then. Oh, so then, okay, you know what we gotta do now?
Just plus
Is we gotta substitute these things in.
Do we have to?
Well, that's what it says to do.
You can say any problem. It's the answer.
So, you know, if you're gonna go through that much trouble, why not just substitute these things at the beginning? That's what I was thinking.
Oh.
Why not substitute these things into the equation before you start? Then you just simply have to take the derivative with respect to t.
Yeah.
Yeah, but then the directions say using the methods of dissection. So they want you to use this formula here, which is kind of annoying, but we do it. So we got this, and then we substitute, what is x? So we substitute cosine t there. What do we substitute for y? Sine t. X is there, so that's cosine t. And then y is sine t. So what do we got? Negative 2 cosine t sine t plus 3 sine squared t minus 3 cosine squared t plus 4 sine t cosine t. Now we can simplify. So this term and this term together add up to 2 sine t cosine t. These two terms can be added together. Why don't we factor out a negative 3, and then you get cosine squared t minus sine squared t. And then A, use somebody, that's sine 2t minus, and A, use somebody, that's cosine 2t, so you get minus 6 cosine 2t. No, what am I saying? Minus 3 cosine 2t. Is that the answer?
Yes.
Yeah, so after the first step is just simplify using trig identities. Okay, I really don't like that problem. I don't think you're going to see that one on the test. In fact, probably 1, 3, and 5, that's going to be on the test.
That's it?
Yeah. Because I'm not a fan of that thing right there.
Okay, did you have this correct?
Okay, this is taking longer than expected. Okay, the gradient as a normal. In fact, you know that thing, the steepest ascent thing? I'm not really a fan of that either.
Okay.
That might not be on the test, probably not. Okay, huh?
Oh, I said okay.
Okay, but now, this is what I was talking to you about before. Writing the equation of the tangent plane. In fact, I'm just gonna go straight to a problem.
Is this the cream of the cream?
What?
Cream of the cream.
Milk of the milk of the section.
Yeah, this is the beginning of, you know, when you have a surface, how do you compute the maximum and minimum points? That's what we're doing.
Well,
But-
we're doing that already.
No, that's gonna be the next section.
Oh,
No, it's really involved, you know, the math, you guys have no idea. You guys have no idea how, because, okay, let's go back to two dimensions. Like, here, I'll give you a simple one. Y equal, how about x cubed minus 3x plus 2? How do you compute the maximum and minimum points of this function? You take the derivative, 3x squared minus 3, you factor it, then you can use either the first or the second derivative test, right? So the first derivative test is you make a number line. -1 and 1, plus, minus, plus, y is increasing, decreasing, increasing. So there's a local maximum here, and there's gonna be a local minimum there, right? In 2 dimensions. Well, what about in 3 dimensions? How do you figure out maximum and minimum points? Or higher dimensions for that matter? It's not, believe me, it's not gonna be that easy. Because think about it, how do you make a number line in 3 dimensions? No. So, the first order of business is, okay, we have a 3-dimensional thing. How do we write, okay, let's do a simple graph then. Z is equal to x squared plus y squared. What is this graph? No.
Elliptic, nice. Paraboloid.
It's a paraboloid.
Oh,
Elliptic, but then it's a circular one, so we just say paraboloid, yeah? So it's kind of like this. Okay, let's say at a particular point, somebody give me a point on this paraboloid.
1, 1, 1. 1, 2.
Okay, let's make it a little more, you know,
2,
2, 2,
different.
8.
How about 2,
3, 4, 5.
1, 5?
Oh, wait, no, that's wrong.
Okay, at this point, write the equation of the tangent plane. Now, in 2 dimensions, we know how to write the equation of the tangent line, right?
Yeah.
Okay, but in 3 dimensions, how do we write the equation of the tangent plane?
great.
The gradient, exactly, because remember in a previous lesson I told you the gradient is simply the perpendicular vector, I'll call it normal vector, and
I still don't understand that. Like,
Why is it?
ridiculous?
Oh.
okay, let me think of a way to explain that. Okay, but while I think about it, let's just do it, okay? So, this is what you need to do, like I remember I told you how you move the z on this side, so you gotta make one side 0 like this. So you kinda gotta move the z on this side, and then think of that as f. That's your function. So, what's the gradient? What's the partial of this with respect to x?
2x, 2y, 1.
Oh, you're good. Here you go. Everybody get that? So at this particular point, what is the gradient vector? At that particular point. What happens when I plug in 2 for x, 1 for y, and 5 for z?
4, 2.
4, 2, -1. That is the perpendicular vector. Therefore, what is the equation of that tangent plane?
4x
4x plus 2y minus z
plus b.
plus d equals 0. And how do I figure out what d is?
Plug into
You plug in the point. So if I plug in 2, 1, 5, you get 8 plus 2 minus 5 plus d equals 0. So therefore d equals -5. So therefore the equation of this tangent plane is 4x plus 2y minus z minus 5 equals 0. I'd rather put the 5 on the other side and make it positive. I don't know why, so for some reason it makes it look nicer. So it's pretty easy, it's very mechanical. Okay, that's the answer, that's the equation of this tangent plane. So the gradient gives you the vector that's perpendicular to the tangent plane. Now as for why that is, I gotta think about it some more. Okay, now, there was a problem. Now, some of the problems are two-dimensional. Like here, look at number 1, it's two, even number 3. In fact, 1 through 7, they're all two-dimensional graphs, but they don't want you to use two-dimensional calculus. They want you to use this gradient thing, yeah? So do the problem this way. Okay?
Here's our menu chocolate.
Yeah, I bought this on Amazon for $7.
$7.
That's how much it costs, man.
For only one of them?
Yeah, I thought I was getting 2, but they only said 1 or whatever. Okay, here, this is what we're gonna, look at problems 18 to 22. Find the point or points on the surface where the tangent line is horizontal. Because think about it,
Tangent line or
If-
tangent plane?
tangent plane. If you have, let's say we're trying to locate a maximum or a minimum point, local maximum, local min. Think about it, like right here. Like if you have a parabola like this. Wouldn't the tangent plane be horizontal like that?
At the vertex?
Yeah, yeah. But then it's not always a vertex, it could be like this wavy thing, right? So anytime you have a maximum or a minimum point, assuming that it's differentiable, then we're looking to see where is the tangent plane gonna be horizontal. Now think about that. If the tangent plane is horizontal, what can you say about its perpendicular vector or the gradient?
0, 0, 1.
The x and the y component are gonna be 0, right?
And it's in the y. Oh yeah, finish.
Yeah, the z component can be anything it's 1, but if the x and the y component are 0, so think about it like in 2 dimensions. What do we call these points that we put on the number line? When the derivative is 0, we call those
Maximum.
critical points. So at each critical point, how do we determine if there's a max or a min? We can do the first derivative test or the second derivative test. Now, do you guys remember the second derivative test? Okay, what is it?
Uh,
The F prime.
You take the second derivative. What's the second derivative of this?
6x.
6x. So, these are called critical points when the first derivative is 0. If the first derivative is 0, which it is, and then you plug it into the second derivative, what do you get?
Negative 6.
-6. And the second derivative is negative,
It's a
Yeah, the
max.
max.
it's a local maximum, because if the slope of the tangent line is 0, and the concavity is downward, isn't that a local maximum? That's called the second derivative test. So we have 2 tests to determine whether you have a max or min. And the same is gonna hold true in 3 dimensions as well. Okay, so the first order of business, we gotta figure out when will the gradient be horizontal. That means the x and the y components are 0. So, why don't we do, I don't wanna do the starred ones, I'm gonna do the ones that are not starred. Or do you want me to do a starred problem?
Yeah.
Start.
No, but then you guys got the answer for that.
Okay.
Can you do number 19?
That's starred.
Yeah, but we can check the answer.
Yeah.
No,
Well, you
yeah,
can do it.
no, you don't. You guys are gonna do that. I'm gonna do the number.
22.
You're gonna do it.
Does that look difficult?
For 22?
They all look about the. They look like all the same
You
thing.
did 21 because it looks super simple, but.
Okay, let's do 22 then. X plus y plus z plus xy minus x squared minus y squared equals 0. See, look, they made one side 0 for you. So think of that as f. So what's the gradient? What's the derivative with respect to x?
1 plus y.
1 plus y
That's 2x.
minus 2x.
Comma.
And then, what is the partial with respect to y?
1
1
plus x.
plus x minus
Plus
2y. What's the partial with respect to z?
1.
1, but we really don't need that, right? Because remember, if it's going to be horizontal, the gradient, the x and y component is going to be 0. So this has to be 0, and that has to be 0. Okay, now what do we do with that? We're trying to find the points on this curve here.
2 variable, 2 ingredient.
Okay, very good. 2 equations, 2 variables. So how do you want to write this? 2x minus y equal 1.
Why don't you just do y minus 2x equals x minus 2?
Yeah, but then you still have 2 variables and 1 equation. We're trying to solve, yeah? So if x minus 2y equal -1, I don't care how you solve it, you gotta solve it. What do you wanna do? Multiply the first equation by,
2.
or multiply the second equation by?
2.
Okay, I'm gonna multiply the second equation by 2. 2x minus 4y equal negative 2. Take these two equations and subtract them, and you get, subtract. 3y equals 3. Oh, y equals 1. Take it and plug it back, okay, plug it back into the first one. If y is 1, 2x equals
2.
2, so x equals 1. So we know that the tangent plane is going to be horizontal at the point 1, 1. How do I figure out the z coordinate? You plug it back into the original, so let's do that. So you get 1 plus z plus 1 times 1 minus 1 squared minus 1 equals 0. So boop, 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 z equal negative 1. So at this point, the tangent plane is going to be horizontal. Now, does that guarantee a max or a min? No, it's a possible max or min. Now, in 2 dimensions, we call this a critical point, but in 3 dimensions and higher, you know what we call this? Joe, since you ran ahead?
Saddle point?
No, it's called a stationary point. Stationary point is a possible maximum or minimum point. And then we have tests we can do to figure it out, and it's going to be really involved, believe me. So just like, okay, just like in 2 dimensions, just because the derivative is 0, does that mean there's going to be a max or min there? No. What about y equal x cubed? I keep bringing this one up. Here's y equal x cubed. What is the derivative? X cubed. What is the slope of the tangent line right there at the origin?
0.
It's 0. So the slope is 0, but there's no max or min there. So that's why it's a possible max or min. So same thing. The tangent plane can be horizontal, but maybe there's not a max or min there. So that's why we have to do these tests. But we're not going to worry about that till next time. So all you have to do is figure out the point where the tangent plane is going to be horizontal. Can you guys do that? That's pretty mechanical, yeah? The answer is yes. So tonight's homework should be pretty easy. Oh, look at 17. I like that cut. That's the kind I like. Okay. Even 19. 19 looks like a good test problem. Okay, let's stop the video. Jason, where